Hello, chemistry students. Today we're going to talk about synthesis and decomposition reactions. In the last lecture, we talked about single replacement reactions. And while those are somewhat different than these, they are both redox processes, and we're going to study them by splitting them up into half reactions and looking at the transfer of electrons between elements. So like I mentioned, synthesis and decomposition reactions are another type of reduction slash oxidation process. And for synthesis reactions, it's when you have pure substances combining to form a compound. A good example of this would be pure hydrogen combining with pure oxygen to make water molecules. Whereas a decomposition reaction is the opposite. It's a compound breaking apart into pure substances or simpler compounds, like water molecules splitting up into hydrogen and oxygen gas. So like I mentioned, we can split these up into half reactions. For the synthesis of water, we start with neutral hydrogen and neutral oxygen, making a water molecule. And while water molecules aren't exactly ionic, we can talk about the hydrogen as being +1 charged and the oxygen as being 2- charged when we split it up. So we start with neutral hydrogen, 2 of them, and that is turning into 4 H pluses because we have 2 times 2 H's in the 2 water molecules. And since we have 4 total hydrogen atoms that are starting neutral and becoming positive, each of those is losing 1 electron. So we have a loss of 4 electrons overall, which means that hydrogen in this case is being oxidized. For the oxygen, we are starting with a 0 charge and becoming 2O2-, which means that each of the 2 oxygen atoms is going to be gaining 2 electrons so that they can go from 0 to 2-. So since there's 2 of them, that's going to be a gain of 4 electrons overall. And that means in this case, oxygen is being reduced. And in this case, oxygen will be gaining the electrons that hydrogen is losing. And since I said that the decomposition of water is going to be basically the opposite process, the half reactions are going to look exactly the same, except in reverse. Now we have hydrogen gaining electrons to become neutral hydrogen, hydrogen being reduced, and then oxygen giving up 2 electrons to become oxygen neutral and being oxidized. In the video here, which I'll link in the description, is an experiment of the electrolysis of water in which electricity is being used as a source of electrons to cause a redox reaction. And in this, you can actually see the decomposition of water molecules into hydrogen and oxygen gas. All right, let's look at another example. Say we have a synthesis of iron 3 oxide. This is kind of what rusting looks like because we have pure iron metal combining with oxygen to make iron oxide, which is one of the compounds found in rust. And here I've balanced it, so we have 4 irons plus 3 oxygens making 2 iron 3 oxides. Let's write the oxidation and reduction half reactions for this process. So the iron is starting at a 0 charge, and in the compound, we can say that it is 3+ charged because oxygen is going to be 2-, and there are 3 of them, so that's 6- over here. And then we have 2 times 3+ to get 6+ to make sure that the compound is neutral overall. So we have 4 iron, which start with a neutral charge, becoming 4 iron with a 3+ charge, which means that each of the individual iron atoms is giving up 3 electrons. And since that's happening 4 times, that is a total of 12 electrons being lost. So that we could say iron in this case is being oxidized. For the oxygen, it's starting neutral and becoming O2-. And since each oxygen is going to be gaining 2 electrons, and this is happening 3 times 2, 6 times, that's a total of 12 electrons being gained by oxygen. And we could say that oxygen in this case is being reduced. So the iron is giving up 12 electrons, and then the oxygen is gaining those 12 electrons in order for the redox reaction to occur. Let's look at another one. Let's look at the decomposition of manganese 2 nitride. So we have Mn3N2 solid breaking up into neutral manganese and neutral nitrogen. So let's write this as oxidation and reduction half reactions. So the nitrogen is going to be starting as a 3 minus charge in this because that's the normal ionic charge of nitrogen, and it's going to be ending at 0. So each nitrogen is starting at 3 minus and then becoming 0, which means that each nitrogen is giving up 3 electrons. And since this is happening twice, that is 6 total electrons being given up by nitrogen. And since we start with manganese 2 plus, which we also know because of the naming, it's manganese 2, is becoming neutral manganese, which means that each manganese atom is gaining 2 electrons. And since that's happening 3 times, that's a gain of 6 electrons overall. So nitrogen is being oxidized, it's giving up 6 electrons, and manganese is being reduced, gaining those same 6 electrons. Let's look at another example of the decomposition of aluminum chloride. So we have 2AlCl3 becoming 2 neutral aluminum and 3 chlorine molecules. And we're going to write the oxidation and reduction half reactions. So the chlorine is starting as Cl1 minus, that's the normal ionic charge of chlorine, and it's becoming neutral chlorine, which means that each chlorine atom is going to be giving up 1 electron to go from -1 to 0. And this is happening 6 times. So we start with 2 times 3 chlorines in the compound, and we end up with 3 Cl2s. So there's 6 individual chlorine atoms here. Each of them is giving up 1 electron, which means a total of 6 electrons are being lost, and chlorine is being oxidized. The aluminum, on the other hand, is starting as a 3 plus charge, since we have 3 minus from the 3 chlorides. So the aluminum must be 3 plus to balance it. We start with Al3 plus. It's becoming Al neutral, which means each of the aluminum atoms is gaining 3 electrons. And since that's happening twice, that's a total gain of 6 electrons overall. And I haven't mentioned it yet in this video, but remember that when you write your redox half reactions, the electrons need to be balanced in both. If you don't have the same amount of electrons in your oxidation half reaction as you do in your reduction half reactions, that means something might have gone wrong with your balancing or the way you set up the half reactions. So make sure to double check that every time. All right, let's look at one more example of the synthesis of lead-4 phosphide. So we start with neutral lead metal and neutral phosphorus solid reacting in a 3:4 ratio to make lead-4 phosphide, which is going to have a compound formula of Pb3P4. And let's write the oxidation and reduction half reactions for this. So the lead is starting neutral and becoming lead-4 plus, which means it's being oxidized because it's going from a 0 charge to a 4 plus charge. So each individual lead atom is giving up 4 electrons. And since this is happening 3 times, that's a total of 12 electrons being lost by lead. Whereas the phosphorus is starting neutral and ending up as phosphorus 3 minus, which is the normal ionic charge for phosphorus, which means that each individual phosphorus atom is gaining 3 electrons to go from 0 to 3 minus. And since that's happening 4 times, that's a total of 12 electrons being gained. So phosphorus in this case is being reduced. And phosphorus is going to be gaining the 12 electrons that the lead is losing. So hopefully that was helpful to help you understand synthesis and decomposition reactions, and I'll see you in the next video.